Good morning, good afternoon, and good evening. Welcome to the Crazy Hat Chemist. So here we are with another awesome video. Last time we were talking about periodic trends, and today we're going to continue. This is part 2 of 2. This is periodic trends. I got this beautiful periodic table behind me, so let's get going on ionization energies. So as you can see there right on your screen, you can see ionization energies. And let's look at some of these numbers here. So you can see as you go down a group, let's take a look at group 1. And where is group 1? I got my pointer, handy dandy pointer here with me. Here is group 1. I know hydrogen might be just slightly off your screen, but hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. That would be group 1, which are the alkali metals, excluding hydrogen are the alkali metals. So if you look at that on your screen there, you can see that the values for ionization energy are 520 for lithium, 490 for sodium, 420 for potassium, 400 for rubidium, and 380 for cesium. So it appears to me that they are decreasing as you go down a group. Another one. We're going to take a look starting with potassium, which is period 1, 2, 3, 4, period 4, then calcium, scandium, titanium, vanadium, chromium, manganese, etc. So if you look at those numbers, that's 424 potassium, 590 for calcium, 630 for scandium, titanium is 660, and vanadium is 650, chromium is 660. You should see those are increasing as you go to the right. So just to recap, as you go down a group, they are decreasing. As you go to the right within a period, they are increasing. So down a group, let's try that out. Down a group, down a group, decreasing. To the right within a period, increasing for ionization energy. The other thing we need to know is what is ionization energy? All right, let's see if we can figure out that. So ionization energy is the energy required to remove an electron from an atom or an ion in the gaseous state. It's that simple. The energy required to remove an electron from the atom or an ion. Okay. So these are first ionization energies. Those values that I gave to you just a moment ago, those are in kilojoules per mole. Even if you don't know what kilojoules per mole is, that's not a problem. We're just looking at those raw numbers. And right now, no, you don't have to memorize those. So don't worry about that right now. If you don't know what kilojoules per mole is, you can imagine those as dollar signs, and then you'll get the same exact concept at least. That's what you're looking for. All right, so you should see that ionization energy increases as you go up a group, and ionization increases as you go to the right within a period. So overall, ionization energy goes up, up, up as you go up and to the right within a period and a group. Hopefully that makes sense. Hopefully you like the Shazam there. All right, let's move on to the next one here. Here we go. All right, so the next one is talking about successive ionization energy. So what we're going to do is we're going to remove one electron, then we're going to remove another one, and then the next one, and then the next one. We're just going to keep on going until we removed all the electrons. So you should see on the left-hand side of your screen, it says EI1, EI2, EI all the way to 7. Okay, so we're going to look at these vertical columns. The first thing we have is sodium. Okay, and what you want to do is correlate these to your periodic table and the number of valence electrons, and the valence electrons are corresponding to the group in which you are in. So what we're going to do is we're going to take a look at sodium. Where is sodium? Sodium is in group 1. There is sodium. So how many valence electrons in sodium? Hold up that finger right now, folks. You can do it. That's right. 1. 1 valence electron in sodium. I knew you could do that. So, how much energy does it cost to remove the first electron in sodium? 496 kilojoules per mole. Okay, now what you have done is you removed all the valence electrons in sodium. The only electrons that remain are core. It's kind of like an apple, right? Does anybody eat the core to an apple? I don't. Do you? Do you? Do you eat the core to an apple? That's a no. Nobody eats the core to the apple. So those core electrons are going to be protected. okay? If you are going to eat those core electrons, it's at a very large cost. So only valence electrons are going to be removed. So after you remove the first and only valence electron for sodium, you should see that the next electron, the next ionization energy, is 4,562. Boom! That's a huge jump in ionization energy. So we won't do that. That's why that doesn't happen. That's why sodium only forms a 1+ cationic state and not a 2+. All right, let's look at another one. Let's look at magnesium. Well, where is magnesium? Magnesium is right there, folks. That is in group 2, which are called the alkaline earth metals. So magnesium is in group 2. So how many valence electrons does magnesium have? 2, because it's in group 2. Who came up with that? Dmitri Mendeleev. That's why we're studying periodic trends. So, ionization energies. Sequential. So the first ionization energy for magnesium is 738 kilojoules per mole. That's pretty easy. That's the first one. The second one is 1,451. You might think, gosh, that's double the first one, but it's still a valence electron. It's an increase, and there are reasons for that. The effective nuclear charge is increasing. You have fewer electrons to hold on to, that kind of thing. So you're pulling those electrons in tighter, but that's not what you need to know. What you need to know right now is that the first ionization energy is low. The second is higher than the first, but still relatively low. Because once you remove that second, now you only have core electrons. So that's why the third ionization energy, that's EI3, that's why that one is 7,733 kilojoules per mole. That's a boom! That's a huge jump. You can't do that because that's a core electron. Each subsequent electron, no way, no how. Okay, check it out. Here's our next one, and that is aluminum. Now, where is aluminum? Aluminum is way over here. It is in group 3 or 13, however you look at that, depending on which your teacher or professor looks at that periodic table. So aluminum has how many valence electrons? Hold those up for fingers for me. 1? No. 2? No. 3? Oh yeah. 3. Okay, so that magic number 3, there are 3 valence electrons for aluminum. So that's why the ionization energy, the first ionization energy, is 578. That's low. The second ionization energy, 1,817. That's higher than the first, but still low. The third ionization energy, 2,745. That's still low. And then, boom! Why does it go up so high? Because that fourth ionization energy for aluminum specifically is a core electron, and you don't want to do that. No way, no how. Okay? So, just let's go over a recap here. If you have any group 1, any alkali metal, what will their first ionization energy be? Low. Second ionization energy, huge, high. How about group 2? First ionization energy low, second is higher than the first, but the third one, boom, through the roof, baby. All right. Then we have boron, aluminum, germanium, anything in this column over here with aluminum. The first ionization energy is low. The second is higher than the first. The third ionization is higher than the second. And then the fourth ionization energy, to the roof, baby. All right, now you got ionization energies, sequential ionization energies. Hopefully you can follow that along. All right, before we carry on with electronegativity, I need a sip of water. How do you like my jug here? Well, it's just a hydro flask, and I've got my label right there. Boom, beautiful. Okay, so the first thing is, what is electronegativity? So electronegativity measures the strength at which atoms attract valence electrons in a chemical bond. So in order to have electronegativity values and have them really play any kind of role, you have to have a bond with another element. It's an arbitrary scale from 0 to 4. This is the Pauling scale of electronegativity values. So let's just take a look at fluorine. So where is fluorine on our periodic table? It is right there. It's a halogen. Fluorine has an arbitrary value of 4.0. So you imagine that you have a GPA with a non-weighted GPA. What's the highest GPA you can acquire? That's a 4.0. All right, now you're going to look one element to the left of that. That's oxygen. That will be the next grade level of a 3.5. The next element to the left of oxygen, nitrogen, that has a value of 3.0. And then carbon, next grade level down, 2.5. Then boron, the next grade level down, 2.0. Okay, now there's a couple that are really important that have the same electronegativity value. And that is chlorine and nitrogen both have a value of 3.0, and sulfur and carbon both have a value of 2.5. The other one that you need to pay attention to is hydrogen at 2.1. So if you've been following me so far, you should see that electronegativity increases as you go to the right within a period. We just did period 2 of many elements. It increases as you go to the right. What else also happens? It increases as you go up a group, and we looked at that with chlorine and fluorine. So, fluorine is the greatest in electronegativity, then oxygen, and then nitrogen and chlorine follow that same trend, and then carbon and sulfur, and then of course hydrogen is really important. One other one as a reference is cesium. In this lower left-hand corner right over here, there's cesium, and that has the lowest electronegativity value of 0.7. So, the trend is as follows. As you go up a group, it increases in electronegativity. As you go to the right within a period, it increases in electronegativity. So therefore, what happens, it goes up in that direction on the periodic table. That is, it increases as you go up and to the right within a group and a period. All right, good, got that. All right. Let's go with the next one, which is electron affinities. Now, if you have an affinity towards something, that means you'll like it. And this is all this means, is when atoms want electrons. When atoms want electrons. So if you have an affinity towards something, like I have an affinity to, teaching chemistry. I love teaching chemistry. I have an affinity to drinking water. I like water. Yeah. So if that's the case, then of course you have a high electron affinity. These are negative values, but the higher the negative, the more you like electrons, because electrons are negative. Let's just keep it that way. What is the highest in electron affinity? And that is chlorine, not fluorine, but it's chlorine. Fluorine is the second. Okay, chlorine number 1, fluorine number 2 on electron affinity. Okay, so that's why I circled chlorine right there. And you should see that the electron affinity increases as you go up a group and increases as you go to the right within a period. And therefore, the overall net is just like ionization energy, just like electronegativity, and just like electron affinity. They all follow the same trend. Hey, that's not so bad. It's super simple. Did you get that? Did you get that? Did you get that? And did you get that? I bet you got that too. All right, good. All right, now what we're doing is we're going to look at the number of valence electrons on the periodic table. I had mentioned that already earlier, but now what we're going to do is you're going to get out a periodic table and write these down. Do you have a blank periodic table? Pause me for just a moment so you can get yourself out a blank periodic table. All right. While you're getting out that periodic table, quick little advertisement break. I am the Crazy Hat Chemist. This is the place where you are to learn all the basics of chemistry so that you can perform well in college chemistry. So if you really are looking for that basic level of understanding for college chemistry, go and look at all my YouTube videos on honors chemistry. If you're looking for a college chemistry, then go look at my AP. All right, quick little advertisement. If you like this video, give me a thumbs up. If you want to make comments, please make a comment. I greatly appreciate that. I'll answer those comments if I get any. And then also please subscribe. Have your cat subscribe. Have your cousin subscribe. Have everyone you know subscribe. Have your mom, your dad, your aunt, your uncle. Have them all subscribe to my YouTube channel. And please tell people in other countries. That would greatly be appreciated. All right, now that we had our advertisement break and you got yourself a periodic table, we're going to write on your periodic table the number of valence electrons. Here we go. Okay, valence electrons are the largest principal quantum number. That is, the N is the largest principal quantum number. And S and P only. Okay, so in column 1, that is the alkali metals. How many valence electrons? 1. So group 1, 1 valence electron. That's why it's called group 1, because it has 1 valence electron. Ha! Who came up with that? Dimitri. Okay, column 2, group number 2, the vertical column group number 2, that would be the alkaline earth metals. They have 2 valence electrons. And then group number 3 or 13, and that starts with boron, and then carbon, 4 valence electrons, nitrogen, 5 valence electrons, oxygen has 6, fluorine has 7, and the next column, excluding helium, has 8. Perfect. All right, now remember, way back just a little bit ago, on part 1 of this video series, you folded out the F's and you folded out the D's and you slammed the S and the P's together. That is, you got satisfactory passing grades in chemistry. Now what we need to do is pull out the F's and the D's, bring them back into play. We don't really want them as grades, but we need to play with them, and we need to figure out how many valence electrons are in there. That would be 2. So how many boots am I wearing? Well, that is 2. So how many valence electrons in the D's and the F's? Well, you know why there's 2 valence electrons in the D's and the F's? Because those grades are going to walk right on out the door, because they're not ready for chemistry quite yet. All right, so that's why there's 2 boots for walking. And you can actually listen to that song by Frank Sinatra's daughter. These boots are made for walking, and walking they will do. One of these days, these boots will walk all over you. Boom, 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 boom. I don't know. You can listen to the song. Anyways, there's 2 valence electrons in the D's and the F's. That's all you need to know. Yeah, get those walking boots on out for those D's and those F's out of a chemistry class. Get them walking on out. All right, here we go. We got some group names that we need to discuss and go over on the periodic table. Go get yourself another periodic table. I won't bore you with another advertisement. You can pause me instead this time. All right, so group names. Here we go. This group is the alkali metals, excluding the hydrogen, because hydrogen is a non-metal, so that's out of this group. It is part of group 1, that is hydrogen. It has 1 valence electron, that is hydrogen. That's why it's in there, as well as everything else in group 1. But excluding hydrogen, the rest of everything in group 1 are called the alkali metals. All right, cool. Group 2 are called the alkaline earth metals, the alkaline earth metals. Now, alkali and alkaline mean the same thing. It means basic. That's opposite of acidic. And so if you were to put any group 1 or group 2 in a water solution, it will immediately react, especially group 1, and will react with water and form hydrogen gas and then a basic solution. You should watch one of my other videos in the demonstration video area, and you'll find out one about these. All right, then there's uranium. That is element number 92. You can find that on your periodic table. That is the highest atomic number of any element that has that is naturally occurring. That's in the universe. Amazing. Anything after uranium is called trans-uranium. That's after uranium. So it has an atomic number greater than 92. That's trans-uranium. Boom. Easy. Okay? Then in the F block, the first top section of the F block are called the lanthanides. The second section, the bottom section of the F block, they're called the actinides. Together, the lanthanides and the actinides, they're having their own F block, and those are called the inner transition elements because they fit inside the D's. That's why they're the inner transition elements. Okay? The D block are called the transition elements. No way. So the inner transition elements fit within the transition elements. And that's why this 57 fits right here, right there. That's why this little sign right there goes here. That's why these two go right there. That fits right in that spot right there. All right, then on the far right-hand side of the periodic table, we have the noble gases. When I was going to school many years ago, I mean like thousands of years ago, because I'm that old, okay, the noble gases used to be called the inert gases, but we have since discovered that the noble gases, actually some of them do react with other elements. Now, There are no compounds with helium or neon, but there starts to be, I think, one compound with argon, and then quite a number of compounds as with xenon, and as you move down the group. The next group, moving to the left from the noble gases, are called the halogens. So that is the fluorine, the chlorine, the bromine, the iodine. Those are the halogens. Those are really important. When those form ions, they're called the halide ions. Okay? All right, now what we're going to do is we're going to talk about periodic trends with oxidation numbers, or their specific charges of what their ionic charge would be when they either lose electrons when they're metals, gain electrons when they're nonmetals. Let's find out what these oxidation numbers are. Okay, here we go. These are predicted charge on ions. There may be some that differ from these, but we're going to go with the predicted charges. Again, these are trends. These are not absolutes. These are only trends. All right, so in group 1, how many valence electrons? 1 valence electron. Why 1 valence electron, and why 1 positive charge? So the alkaline metals and hydrogen will lose 1 electron to form a 1+ cationic state. A cation is something that has a positive charge. All right, then we have group 2, the alkaline earth metals, and that has everything there. They lose 2 valence electrons, and the loss of 2 valence electrons, of course, will have a 2+ cationic state. So we've gotten 1, we've gotten 2. Now we're going to go 3, and then 4, and then what's the Roman numeral for 5? V for victory, and that's for vanadium, and that's why that right there, V for victory, and we've got Roman numeral 5, and that's a 5+. All right, so we've counted 1, 2, 3, 4, and 5. Now that we've counted 5, we're going to count 5 again, because we keep on counting 5. So what we're going to do is we're going to count right after vanadium. We got chromium, manganese, iron, cobalt, and nickel. That's 5 more. So these 5 all have the same 2 charges. So these have 2 charges to them. There's a 2+ and a 3+ for chromium, manganese, iron, cobalt, nickel, and I think I got all those on there. Chromium, manganese, iron, cobalt, nickel. Yeah, that's 1, 2, 3, 4, 5. Boom. All right, now let's say that you're driving down the freeway and you see some lights behind you because you've been driving too fast. Who is behind you? Well, who's going to pull you over? That would be a copper. There's a picture of an old copper right there on the screen. So what is that copper going to make you do if you see those lights? He's going to make you pull off on the gas and start slowing down a bit. So that's what you need to do. So you've been traveling at a speed of a 2+ and a 3+. So you need to decrease your speed on each of the 2 and the 3 by 1. So 1 minus 2 is 1, and 1 minus 3 is 2. So that means that copper right there has a 1 and a 2+ cationic state. All right, the next one here is we're going to do a diagonal pattern of silver, zinc, and aluminum. This is a very famous pattern of a diagonal pattern here of silver, zinc, and aluminum. So silver is a 1+, zinc is a 2+, and aluminum is a 3+. All right, fantastic, got those. And now you have cadmium right underneath zinc. Since they're in the same column, they have the same charge of a 2+. All right, then there is gold. Now, silver and copper have a common charge, that's a 1+. Gold also has a common charge because it's in the same group or family. It also has a 1+. But gold is worth more, so that's why it has the higher charge. That's not actually true. I mean, gold is worth more, but it's not worth more because it has a higher charge. But hopefully that just gets you just to memorize it. All right. Then, right next to gold, to the right of gold, we have mercury, there's the only liquid metal at room temperature and pressure. And mercury has a combination of 2 charges. That's what the column is a 2+, and then what the previous column was, that's a 1+. So it's a 1+ and a 2+. All right, we're almost there. We're like 3/4 of the way there. All right, the next one is this 3+ in this column, starting with boron. That's where the aluminum is, so that should make sense for you. We have a 4+ for carbon. That's not so bad either. Okay, then we have tin and lead. Tin and lead have a 2+ and a 4+. Boop, done. All right. And then we have the noble gases. This is one of the greatest mistakes here that people do, is they put the noble gases as some kind of charge. Well, they don't react with other elements, so let's give it a big fat 0. So if you don't want to react with other people, be a noble gas. Be noble, okay? Then the halogens, or the halide ions, eventually, that's why they're called the halide ions, because they have a -1 charge. That's fluorine, chlorine, bromine, and iodine. That's a -1. Then oxide in that column has a -2. Nitride in that next column, -3. We just about got all the oxidation numbers of periodic trans. Now, some of these do not follow these, and some of them have multiple charges. Like, I know that vanadium has a bunch of different charges of oxidation numbers. Same with nitrogen. So if you go on to other levels of chemistry, you might be like, whoa, Mr. Montbrion, you're wrong, man. Crazy hat chemist, you don't know what you're doing. I do. I'm just getting you to teach. I'm just getting you to learn the trends, because we're all about trendy. I mean, that's why I'm wearing this sweater right now, because it's trendy. Not really. All right. I'm hoping you're learning something here. Give me a thumbs up, and I'm going to see you next time for the next video on whatever that may be.